Today we have a very, very interesting case in our clinic. It has to do with the interplay between glycolysis and the pentose phosphate pathway. So someone asked the question, is it possible to have these two pathways active at the same time? Now, this is a very interesting question. Both pathways have to do with degradation of glucose. So they start with glucose. Glucose is converted to glucose 6-phosphate by hexokinase. Now, at this point, there are two things that are expected. The glucose 6-phosphate is going to continue down this road in the glycolytic pathway to produce ATP for the body, or the glucose 6-phosphate will go this way into the pentose phosphate pathway to produce NADPH and ribose 5-phosphate. Which is which? What happens at what time and for what reason? Now, whatever happens to this substrate, glucose 6-phosphate, entirely depends on the needs the body needs. What does the body need more at that point? Is it ATP? Well and good. So glucose 6-phosphate will proceed in the glycolytic pathway to produce ATP. Is it NADPH that is needed more than glucose 6-phosphate is going into the pentose phosphate pathway? Now, there is a very interesting question, probably the reason why this question was asked. There are times when the body needs NADPH as much as it needs ATP. What happens? Now, what this means is both pathways have to be active in one way or the other. How does this happen? So here's the thing. So when we have a situation where the body needs both NADPH and ATP, so at the point of glucose 6-phosphate, this substrate will be channeled into the pentose phosphate pathway to first of all generate NADPH in step 1 and step 3 of the oxidative phase. And once this is done, you have ribose 5-phosphate being produced. Now, this technically in the non-oxidative phase has two possible routes: to produce ribose 5-phosphate, which is used to make PRPP, or phosphorybosyl pyrophosphate, which is critical in the purine and pyrimidine metabolism, which ultimately produces your RNA and DNA. Or ribose 5-phosphate can be converted to xylulose 5-phosphate, which can be converted to fructose 6-phosphate, an intermediate of glycolysis. In this case, since the body needs both NADPH and ATP, glucose 6-phosphate will first undergo the oxidative phase of pentose phosphate pathway to produce the NADPH that is needed by the body. And once this is formed, we can use ribose 5-phosphate in the non-oxidative phase, convert it to xylulose 5-phosphate, and thereafter convert it to fructose 6-phosphate, which joins the glycolytic pathway at this entry point, thereby proceeding into glycolysis, forming pyruvate, which can be broken down to acetyl-CoA, which can combine with oxaloacetate in the TCA cycle to produce FADH2, NADH, GTP, carbon dioxide, and then the FADH2, NADH will go into the electron transport chain, donate electrons, and thereby generate ATP. And the body is going to have both the ATP and NADPH. So technically, there is an interesting interplay here. So the answer to the question at hand cannot be a direct yes, and it cannot be a direct no, because of the situations that allow these two pathways to have this interplay. I hope that was clear enough. If you have any further questions, please don't forget to leave your question in the comment section and we'll address it in our next clinic. Thank you very much for watching.